welcome to Miss Clarke's chemistry class. This is the 7th lesson on a series of lessons about nuclear chemistry. This lesson, we're going to talk about nuclear fission. Yes, that thing that runs the atomic bomb. We're going to talk about how that happened and why was there so much energy and destruction attached to it. So go get your notes and let's get started. Now, before we talk about nuclear fission, I want to talk about this vocab word called nuclear binding energy. This is not something I've talked about yet. The nuclear binding energy is the energy required to separate the nucleus into its nucleons. Nucleons. I don't think I've said that word in all of the lessons, so it's a good thing you're tuning into this one. A nucleon is the term given to any particles in the nucleus. So this could be the protons and the neutrons. We can just call them nucleons, the particles of the nucleus. And the binding energy is the energy required to separate the nucleus into its nucleon. In previous lessons, we talked about strong force. That strong force, that's what keeps all the nucleons glued together. So the energy required to separate those nucleons, that is a great deal amount of energy here. First, let's talk about like medium-sized nucleus. Medium or small nuclei. They're going to have less nucleons, and that strong force holding them together is going to be greater. So if the nuclei is smaller and the energy it's going to take to pull those nucleons apart is greater, we would say that medium and small nuclei have very high nuclear binding energy. And when the nuclear binding energy is high, that means that the nucleons are very tightly packed together, meaning they're pretty stable. But when we have large nuclei, since there's so many nucleons in the nucleus, the nuclear binding energy is actually going to be a little bit less. So let's show that. Less nuclear binding energy. And when the binding energy is a little bit less, that's what causes these nuclei to be unstable. So really heavy nuclei, really large, heavy nuclei will split into two medium-sized nuclei to find stability. So heavy nuclei with lots of nucleons oftentimes will become so unstable that they split into two. And those two smaller nuclei over here, much more stable. Fission. When we talk about nuclear fission, fission means we're separating. Something is coming apart. Now that energy, when we split into two and become stable, that energy has to go somewhere. So when the heavy nuclei splits into its two more medium or smaller nuclei, it's also going to release a great deal of energy. Let's look at this a little bit more closely. Now, some fission happens naturally. The fission in like today's modern world, most of the time when we're talking about nuclear fission, we're talking about man-made fission. Fission that's happening on purpose. We're inducing this fission. And that's what I'm going to explain right now, is how to induce this fission. So to induce fission, we're going to start with this neutron. We're going to take this neutron and we're going to slam it into a huge, heavy nuclei. And when we slam this neutron into this nucleus, it sticks in there. So we're adding one more neutron to this already big, heavy, unstable nucleus. So we took this unstable nuclei, and by adding this neutron, we made it even more unstable. In fact, it's so unstable, it's going to split into two smaller nuclei. And after this split occurs, these two smaller nuclei, they're much more stable. Not only do we get these two smaller nuclei, we're also going to get debris. We're going to get nucleon particles, oftentimes in the form of neutrons. When this large nuclei broke through the nuclear binding energy to split these into two smaller nuclei, that energy has to go somewhere. This atom is going to release that energy into the atmosphere, and it is a lot of energy. This is a basic fission reaction. We're going to take a large, unstable nuclei. If this is man-made fission, we're going to slam it with the neutron. That neutron's going to stick. It's going to cause it to become even more unstable, so unstable that this nuclei is going to have enough energy rumbling around in the nucleus to split in half. It's overcome that nuclear binding energy, splits in half, shoots out a couple of neutrons, also releasing a lot of energy. But if you think about it, this is one radioisotope. We have one nucleus doing this. We slammed one neutron into one nucleus. How much energy can that really make? Well, not enough to be very useful. But what if we had lots of radioisotopes and we were slamming lots of neutrons into these isotopes, and so we were creating lots of energy? This is where nuclear power plants come into play, or even nuclear bombs. So how can we force this reaction to happen on a big enough scale so the energy that we're producing is actually useful energy? The chain reaction. And what happens, same fission reaction. I'm going to draw this for you, but I'm going to use less dots. Let's say this dot is uranium-235. And if I've got my neutron, and I'm going to slam my neutron into my uranium-35. Now remember, that neutron is going to stick and become uranium-236. I'm going to skip that for now. When we slam it into that nucleus of uranium, 3 more neutrons pop out. Remember a while ago I told you that when that big nucleus splits in half, when it undergoes fission, nucleons also shoot out. In this instance with uranium-235, 3 neutrons. Now those 3 neutrons, they're being shot out of the nucleus at a very high speed. Now what happens if those neutrons hit 3 more uranium, and those 3 uranium shoot out 3 neutrons of their own, which then go and hit more uranium? You can see how this is going to get out of hand very quickly. So when we need to make a lot of energy, we want this chain reaction to occur. Really, when are we ever going to have 1 atom of uranium? We're going to have a chunk of uranium. We'll have millions of atoms of uranium. And so this chain reaction causes you to be able to start a reaction on a small scale. Very quickly it ramps up to full scale. This reaction can get out of hand very, very quickly. This reaction is what made the atomic bomb possible. Learning about this chain reaction and how to induce this chain reaction. We also get nuclear power plants using this reaction. In the atomic bomb, this reaction gets out of control. In a power plant, we want to try to moderate this reaction so we can control it. Now, the example I'm going to show you is uranium. Uranium is the most popular element that's used for nuclear fission. Anything after number 92, like 92 is uranium, 93 is neptunium, 94 is plutonium. All of these really good fissile isotopes. Fissile because they are so large and unstable. I wanted to show you the uranium example, but I wanted to show you how we write this in a chemical reaction looking kind of format. So here's our neutron. We slammed it into our uranium. Remember, our uranium went up by 1 because of that neutron. The atomic number stayed the same because we only added that neutron. And then we get our fission. That breaks into barium-141, krypton-92. There's our 3 neutrons. Now, uranium doesn't always just break up into barium and krypton. It can also break into rubidium-90, cesium-143, but there's our 3 neutrons still. It can also break into strontium-90 and xenon-143, and there's our 3 neutrons still. So I wanted to make sure and show you that elements, when they go through fission, it's not the exact same process every single time. Since we were talking about a nuclear reactor, I kind of wanted to show you a basic schematic on how this works. Our reactor core, let's start there. This is where the nuclear reaction is going to happen. This is where our uranium is going to be. This is where fission is happening. Now we're trying to create energy. And so what we're going to do is we're going to take this cool water. The cool water is going to run through this system. See, this is a closed system here. When this nuclear reaction happens, it's releasing a lot of energy, and that energy is heating up this water. And so when the cold water comes through, it's getting heated up. It turns to steam. The steam exits and powers this turbine. And then that turbine shoots out electricity. Now this electricity could go to a power grid, power lines. It could be in a nuclear sub, and that's what keeps the engines going. Nuclear subs aren't always called nuclear subs because they carry nuclear weapons. Nuclear submarines are powered with nuclear energy, so it can go much longer distances, so it doesn't have to use gasoline or any kind of battery. I want to bring your attention, though, to these control rods, because we talked about in a nuclear power plant, we're trying to control this fission reaction. Fission reactions can get out of hand very, very quickly. That's what happened with Chernobyl. The reactions got out of control. Now you've got to keep this cool. That's where we run this cool water through. But there's also these things called control rods. And you can put these control rods down into the uranium, and it helps slow down the reaction. It makes it to where there's not as many of those free neutrons floating around to slam into other uraniums, these control rods. So when we're talking about wanting to moderate the reaction, especially for a nuclear power plant, 2 ways we could do that. Maybe we just use less uranium. If there's less uranium atoms in the sample, then there's going to be less fission. Also, when we were talking about the chain reaction, you have to have what's called a critical mass. A chain reaction will not occur until you have a critical mass, and that's just the mass of the substance. You have to hit a certain threshold before the chain reaction will actually take hold. So if you don't have enough uranium, you don't hit critical mass, you can't make that chain reaction happen, and the amount of energy that's released is not as great because we don't have all of that chain reaction happening, and so all the uranium is not undergoing a fission reaction. We could also have things called neutron absorbers. That's what these control rods are. So we talked about in the chain reaction how those extra neutrons that shoot out of the nucleus then go and hit other uranium, which cause it to do fission, which shoots their neutrons out, which hits another uranium, which causes them to do fission. Chain reaction, you got it. If we absorb some of those neutrons, if we put some other chemicals, if we put some other elements in the way and they absorb those neutrons before they can go slam into another uranium, that's a way we can control this reaction. Fission is one of those crazy science things that can be like really, really good or really, really bad. Since nuclear fission can either give us a supply of abundance of energy, but as we've seen with the atomic bomb, it can also lead to quite a bit of destruction. Nuclear fission, we're taking a big nucleus, breaking it apart, tons of energy, crazy amount of energy. I still need to talk about nuclear fusion. Meet me back for that lesson. Until next time, bye y'all.